I'm truly honored to have this opportunity to talk here today on a subject that I've been developing since grad school. I graduated MIT 71. I graduated in a grad seminar. Minsky said, you know, consciousness is just this functional schemata. You guys just go out and find it. And so I submitted a thesis proposal to Mike Dertuzos. I submitted that stuff as a thesis proposal, but I only got linear results, and I left academia and spent my career in engineering. And I've done things like, with other people, build virtual realities for torpedoes, for NUSC, and build the world's largest scalable fabrics for both multiprocessors and routers. But now I'm building a fabric for the brain, effectively. It contains a cortical information exchange protocol that I'm working on, and I call it the HaveNWant schemata. It's currently in simulation. It's a Mac app called the Fractal Workbench, and as you guys probably know, there's nothing like simulation to wring the magic out of a dream and leave behind these causal mechanisms that you sure hope work. The purpose of my talk here today is to infect you with these ideas by giving you a little taste of this curious little powerful world of haves and wants. It's all on a website called braingears.blogspot.com, including this presentation. What's driving this work is how does a neuron situate itself in this sea that's the brain? And I think the answer to that is a thing that I'm calling micro-bidirectionality. Bidirectionality pushed all the way down to the 1-bit level. So I've designed this set of, I call them thinker toys, although I think it's copyrighted. It's a kind of tinker toy with cognitive abilities. I intend them to act like this magical intelligence putty. It's a combination of perceptronium, which we saw yesterday, and another one I thought of last night, which is axolot. So this intelligence putty stuff, you smear all over your motors and your sensors, and when it hardens, the system operates better for it. And part of my secret sauce for this involves embedding certain critical abilities into the atomic form. Now, this is a bit slice approach. This is not a big box approach where you have learning algorithm for everybody off on the side. This is every bit of information is doing its part in a real-time network. So if you keep this extra stuff around, you can have learning occur without any extra effort, kind of the way water vapor condenses to form a snowflake. One of these abilities are the n-arm bandit counters that are in every node that tell basically whether it's pulling its weight or not. I believe these whole things can be made very scalable and efficient and stable in terms of the dynamics. What I'm going to describe is a simple bidirectional schemata made up of only 1-bit forms with just an and an or, except they're bidirectional. So although there's a lot of more complicated ways of making these bidirectional forms than I'm thinking of, I'm just going to take the very simple one. So networks can be built up using what I call bidirectional fractal links, and we'll talk about those more, between two nodes. So I'll show how several networks, what each is good at, and I'll show, for instance, how a whole network can operate either forward or backward, how a winner-take-all functionality can be easily implemented, how trees can be used to expand single elements without limit, how attentional mechanisms can be built on top of this, which naturally implement Maslow's hierarchy of needs. I'll show an element that computes the Hamming distance and then use it to make a distributed associative memory. And finally, I'll show a simple example of learning in the information domain of a bidirectional shaft transducer. There are some other network things on the website that I don't have time for. The simplest kind of learning is a Hebbian instantiation. That's, I think, the term that came out of this conference for me. When two unexplained links have a newer node attached to connote their coincidence. So basically, you want to get everything so it's represented by a single node. This is an early video which kind of got me thinking about it, and it shows patterns flashing at the bottom and then new decodes at the top. Other forms of learning are compacting variables. For instance, if you include an extra kind of value in a color variable, or a thing I call volume optimizations, where the network is edited while it's being operated on. So HaveNWant brain is defined as being composed of nodes and fractal links. A fractal link is composed of two scalar variables, a have signal, which connotes evidence that the being has evidence that the fractal is true in the world, and a want signal that connotes that the being has motivation to make the fact become true in the world. You've seen these things before in terms like feed forward and top-down feedback. I give them the names have and want. I think that a lot of algorithms could be restated with this kind of metaphor and actually have some of the interactions driven to better understand it. So everything is represented as a fractal. They're in an ordered graph. You guys know this, where the lowest nodes connect to the motors and sensors, and where nodes at higher levels change slower and are more sophisticated, and at the top there's the beliefs and knowledge about the being. So all information about the world is held in these fractal links. A brain with any amount of common sense might have thousands to millions of these links. Each link corresponds to a particular subset of the world state referred to as its fact. A fact in the graph there might be that pixel 00 is on in the machine's computations. How do you understand what these up and down variables should be used for? What I've determined is it comes down to there's kind of three ways that they can be encoded. The first is kind of in the notion of Bayesian prediction with pi and lambda variables. We've seen a lot of that. You see that all the time. There's also pairs of dual conjugate variables, often related to energy. I've explored one of those in my thesis proposal, and it's interesting because you can show that those can be made guaranteed stable. But then there is another group that I call the excluded middle, and it's pretty agreed that people use this logic of the excluded middle. The excluded middle is where 0 is 0 and 1 is 1 and a half is implementer's choice. You know, it just does something when it's a half. I've uncovered several useful encodings while exploring HaveNWant. Notice that the first of these two are linear, and I actually see that as a limitation. The excluded middle is nonlinear, and let me just pull us off into a two-dimensional world rather than a hyperspace world. If you think of John Conway's Game of Life, it's the nonlinearity in the rules that allow them to flourish and not just fade away like thermodynamics or something like that. I think the same thing happens in these hypercubes that I'm looking at. So let's go through the atomic elements. When you open the box, what do you get? The first kind of thing you get are these things that share information. They're shown in canonic form with one port at the bottom. That's a bidirectional port, and 3 ports at the top. It divides a signal link below into multiple links on the top. And different kinds of shares do different computations. So you can do ands and ors, and there's norms that are in there, and Hamming distances. There's a bunch of different kinds of shares. There's a previous unit that keeps around the state from the past so that state transitions can be detected. And it also manages and determines when you're simulating whether you're simulating backwards or simulating forwards. And there's a gate which modulates the up and down signals, making them more or less poignant. A mirror terminates links, so at the top what you have is what you want. It's kind of an optimism. And at the bottom what you want is what you have. It's kind of a peacefulness. You want what you have. There's other plumbing. Bundles are groups of 1-bit forms, usually with a common target. Variables are bundles. So this is where I'm headed. This is going to get turned into code and built, but is it not today or not for a while? This guy is Super Mario Brothers. This is a visual system which is also on tap. But let's start with something that's much simpler. And it's tracing the have signals as they flow up in this simple network. If we have that it's raining and I have an umbrella, then I have that I'll stay dry. That's pretty simple, but the logic can be turned inside out so that if it's raining and I want to stay dry, then I want an umbrella, and now if umbrella B is nearer, I'll go get umbrella B. There's some interesting dynamic computations that go on that ultimately lead to things like sequencing. The second is a thing called a MaxOr Gate, which implements a winner-take-all in this bidirectional metaphor. So we talk about its have signals, which are computed from its workers as the maximum of the workers have, so that's a simple pass up. And sometime what it does is it looks at those maxes and determines the number of the winner, argmax kind of thing. And then a single winner, if some want comes down, then it goes only to the winner. So this is, the winner gets all of the downward stuff, and everyone else gets nothing. Certainly there's physical limits on the number of ports you can have on a gate, and it turns out that you can make trees of these things and they work just fine. Max is a very kind function. You know, max of a max is a max. You don't care about the order. There's a movie of an early version I made of the Facto workbench. At the bottom there's 5 inputs, and I will start it up, and the mouse is raising the have on the interface, and that's showing in green going up, and then the want says, oh, it goes all to C. Now, if A turns out to have more, then A is the one that gets the max. So this is an interesting operation of tree mechanics that could be useful. And in fact, that will show that's a basis of an intentional multiplexor. So let me go on from here. The functionality of a tree can be expanded by adding an auxiliary bundle of information to each bid to characterize it. In our toy example, it could come from audio information, video, you know, that there's lightning flash, or touch information. It works in 3 phases. The biggest bid goes up the network, the winner is declared down the network, and then the winner then gets turned on in the multiplexer. So what comes at top is the data from the most important thing to be attended to. So this is an attentional mechanism. Now, so you can actually modify the form of each one of those things and do computations so that the auxiliary information for a bid is kind of all the variants of it that it supports, if you would. And that can grow dynamically as the network works. There can be a binding. So I'm the attentional system at the top of this tree, and I want to bind down to this node. And I might do something like say, shut up. So I say that, and he removes his bid. And he removes his data, and he goes away. So I can actually establish conversations that way. And then another guy would come in. So you can play a lot of little tricks like this. My bet is that vast areas of the brain kind of have this kind of architecture, especially in the entorhinal cortex leading up to the hippocampus. This is a MultiplyAnd Gate. Same thing as before, except what it does is it multiplies its. So if any one of them is 0, the output is 0. So what happens is things get distributed on this based on how much the bid is a laggard. The third one to the right, 0.1, is the laggard. And what happens is it captures all the omega, all the credit. So all of the desire to get turned on comes back to it. The laggard thus captures all the credit, and thus all the want goes to the laggard. Bidirectional MultiplyAnd Gate wants their lagging inputs to become true. This property can be used to build an associative memory. So consider what happens when you put a certain input pattern in the bottom, and it is almost satisfies one of those AND gates, the one on the left. So the halves go up. It goes through this Hamming distance. It wins. So it says, yeah, I got someone here that's close. So if someone on high says, yeah, I want you to be true, it goes down and turns the want on to that missing input. So what effectively you've done is you've hallucinated the missing input. And this is a way that you can make associative memories. You can put the current terms on one side, and you can hallucinate the forward progress. So you can turn these things that you learn of by just remembering now and what was before, those state transitions, you can turn it into a predictive memory with this kind of HaveNWant abilities. The final example is a shaft encoder, and a set of 3 fractals and a mechanism which keeps them in sync. So that if the shaft is on A, the node has its A have signal on. This is a basis upon which this understanding is. This is a given if you do an inductive proof. But what we want to do is on top of that build something where we're detecting what rotations are, and that's what the nub of this is. Rotations are detected by state transitions, and state transitions require having the previous value around. So we just add some more fractals on the side that do this previous function that I was talking about before. And now suppose that the shaft goes to B. Well, it's at B, the current. The previous is still back at A. And what you want to do is you want to add a coincidence. This is heavy in instantiation, which basically says if I want to remember all these associations, if I ever get one I don't understand, I'll add elements until I do. So then the shaft moves on to the next, and it fires the next one, and a third time it moves on to that and fires that. Thereafter, it can keep going around, and it will just be detected by those 3 that it's already gotten. Except if it starts going backwards, it's going to get them going backwards, and then they can get another 3. I guess that slide ended pretty quickly, didn't it? So I've described this HaveNWant schemata, and I argue that it should organize itself by adding experiences. I hope to get it working. I say 3 months, but I'm always off by a factor of pi or pi square. So, get it to, I think I should get it to work as advertised. Now, I'd like to understand your perspective on this plan and how you see, what does it look like from that side looking in. So any feedback to that. I, to a certain extent, am this, I went off into engineering land and maintained some contact, but I'm trying to figure out what I got here. Thanks for your attention.